Imagine the entire universe squeezed into a space smaller than an atom. About 13.8 billion years ago, this tiny point exploded with unimaginable force, an event we call the Big Bang. In the first fraction of a second, the universe expanded rapidly, cooling as it did so. The Big Bang wasn't an explosion in space, but rather the expansion of space itself. Imagine a balloon with dots on it. As you inflate the balloon, the dots move apart, just like galaxies in our expanding universe. The Big Bang Theory is the best model we have to explain the origin and evolution of our universe. As the universe cooled, energy began to condense into matter. The first particles to form were elementary particles like quarks, electrons, and neutrinos. These particles interacted with each other, forming protons and neutrons. The universe was still too hot for atoms to form. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to be captured by protons, forming the first atoms. These first atoms were primarily hydrogen and helium, the two lightest elements. They formed vast clouds of gas that spread throughout the early universe. Tiny variations in density present from the Big Bang itself acted as seeds for gravity to pull matter together. These clumps of matter grew denser and denser, eventually becoming the seeds of the first stars and galaxies. Gravity continued to pull matter together within the primordial gas clouds. As these clouds contracted, they began to spin, and the temperature and pressure at their centers increased dramatically. Eventually, nuclear fusion ignited, and the first stars were born. These early stars were much more massive and short-lived, burning through their nuclear fuel much faster. As these stars died, they exploded in spectacular supernovae, scattering heavy elements into space. These heavy elements became the building blocks for planets, life, and everything we know. Over time, gravity continued to sculpt the universe. Smaller clumps of matter merged to form larger ones, eventually giving rise to galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter bound together by gravity. The Big Bang Theory is supported by a wealth of observational evidence. One of the most compelling pieces of evidence is the cosmic microwave background radiation, or CMB. The CMB is a faint afterglow of the Big Bang, a snapshot of the universe as it was just 380,000 years old. The CMB was discovered accidentally in 1964 by astronomers Arno Penzias and Robert Wilson. They detected a faint, persistent noise that seemed to come from all directions, which was the afterglow of the Big Bang. The CMB provides a direct glimpse into the early universe, confirming many of the predictions of the Big Bang Theory. Another key piece of evidence is the abundance of light elements in the universe. The Big Bang Theory predicts specific ratios of light elements like hydrogen, helium, and lithium, which have been confirmed by observations. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This relationship between distance and velocity is known as Hubble's law. Hubble's observations provided the first direct evidence that the universe is expanding. The expansion of the universe is often compared to baking a raisin bread. As the bread bakes, the dough expands, and the raisins, representing galaxies, move farther apart. The expansion of the universe has an interesting consequence: the existence of a cosmic horizon. The cosmic horizon is the limit of our observable universe, the point beyond which light hasn't had enough time to reach us since the Big Bang. While the Big Bang Theory has been remarkably successful, it raises new questions. One of the biggest mysteries is the nature of dark matter and dark energy. These mysterious substances make up the vast majority of the universe's mass energy content. Dark matter doesn't interact with light, but its gravitational effects are evident throughout the universe. Galaxies rotate faster than they should based on their visible matter content, suggesting the presence of dark matter. Dark energy is thought to be responsible for the accelerating expansion of the universe. Observations of distant supernova have shown that the expansion of the universe is speeding up. This discovery suggests that there's something fundamental about the universe that we don't yet understand. The fate of the universe is intimately linked to the nature of dark energy. If dark energy continues to dominate, the universe will continue to expand forever, leading to the Big Freeze. However, other possibilities exist. If dark energy changes over time, the universe could experience a big rip, tearing apart galaxies, stars, and even atoms. Alternatively, if dark energy weakens or reverses, the universe could stop expanding and begin to contract, leading to a big crunch. In this scenario, all matter and energy would collapse back into a singularity, potentially giving rise to another Big Bang. The ultimate fate of the universe remains one of the biggest unanswered questions in cosmology. The Big Bang Theory describes the origin and evolution of our observable universe. But what about regions beyond our cosmic horizon? The multiverse hypothesis proposes that our universe is just one of many within a larger multiverse. Some versions arise from inflationary cosmology, suggesting rapid expansion created bubbles in space-time, each giving rise to a separate universe. Other versions are based on string theory, which suggests extraspatial dimensions could harbor other universes. The multiverse hypothesis is a fascinating but highly speculative idea. It challenges our understanding of the universe and opens up new possibilities for exploration. The vastness of the universe raises a profound question. Are we alone? Astronomers are discovering new planets around other stars called exoplanets at an astonishing rate. Some of these exoplanets are located in the habitable zones of their stars, where conditions might be right for liquid water to exist. The search for extraterrestrial life takes many forms, from searching for biosignatures in exoplanet atmospheres to listening for radio signals from other civilizations. Closer to home, scientists are exploring extreme environments on Earth for clues about how life might exist in otherworldly conditions. The discovery of even simple microbial life beyond Earth would be a profound scientific discovery. The search for extraterrestrial life is a quest to understand whether we are alone in the universe. Cosmology has made remarkable progress in understanding the universe's origin, evolution, and large-scale structure. However, many mysteries remain. The nature of dark matter and dark energy, the ultimate fate of the universe, the existence of the multiverse, and the search for life beyond Earth continue to drive cosmological research. The future of cosmology is bright, with new telescopes, instruments, and missions planned that will revolutionize our understanding of the universe. Cosmology is a journey of discovery, a quest to understand our place in the universe and to unravel the secrets of the cosmos. From the Big Bang to the evolution of galaxies, stars, and planets, cosmology continues to push the boundaries of human knowledge and inspire wonder and awe at the immensity and beauty of the universe we inhabit.